Welcome to Ask Why, a podcast where we decode technology and components and look under the hood of what makes those components function. Today, we started a series last week called Capacitor Confessions, and we talked about aluminum electrolytic capacitors. Today, we're going to continue that session, and we are going to talk about MLCCs and ceramic capacitors. With me here again, I got Peter Blaze, Head of Technical Marketing, and we're going to take another dive into MLCCs. So, Peter, MLCCs, to start off simple, what exactly is an MLCC?
Well, an MLCC is a ceramic capacitor. Actually, it stands for a multi-layer ceramic capacitor. That's what MLCC acronym stands for.
So when I see multi-layer, is it actually just layered capacitors, or what exactly can I understand under MLCC?
So recently I was traveling on vacation, and we went to a pastry shop. And in the pastry shop, they had a cake that was local to the region, and it had very thin layers of cake and then separated by a thin layer of frosting. And this particular cake had quite a few layers to it. You know, when I was growing up, you get a birthday cake, it had 2 layers to it with the frosting in between. This thing must have had a dozen or so layers in it. And so when you look at an MLCC and you chop it across the section of it, and you were to look at it, you would see lots and lots of layers, similar to this delicious cake that was in the pastry shop where I was on vacation. Now, unlike the cake, which had about 12 layers, an MLCC today, leading edge MLCCs can have upwards of over 1,000 layers inside of them. And those layers are going to be made out of the dominant metal used is going to be nickel, which is referred to as base metal electrode. And then you're going to have 2 basic dielectric systems, which is ceramic. It's either going to be barium titanate, which would be for your class 2 ceramics, X5R, X7R would be the 2 main ones. There's other variations. And then you have class 1s, which would be calcium zirconate, which is almost like a porcelain. It's a really hard, durable material. And that is going to be used in our class 1s because it has, to get kind of overly complicated, it doesn't have any domains in its structure, so it has a very low dielectric constant, and therefore it acts nearly as an ideal capacitor as you can get. So those are the basic technologies of MLCCs and the construction, why they're called MLCCs.
So I guess you already dove into a little bit. MLCC is not MLCC. There's multiple different technologies within that, different dielectrics. You mentioned X5R, X7R, COG. What are some of the benefits of each of those technologies? What, as a designer, would I have to consider? When should I use X7R? When should I use COG?
Excellent question. And to answer that, I think we need to back up a bit and understand why you're using the part. So in the last episode that we talked about bulk capacitance and aluminum electrolytics. So MLCCs, class 2s, which would be barium titanate based, X5R, X7R, they can be used, they're used for also bulk capacitance. It just happens that the capacitance value is much, much, much smaller, and their frequency response is also going to be quite a bit higher. But those are used for bulk capacitance in decoupling and filtering, which is really the predominant use of MLCC. So if you take a look at this is being recorded on a computer. If we were to open up that computer, look at that system board, we would see MLCC scattered all over that board on the top side and on the bottom side, decoupling the 5 volts and the 3.3 and the 1.8 and all the way down to 0.8 volts that are distributed throughout that board. And those class 2 ceramics are decoupling those voltage planes. In other words, keeping them very, very stable. And they're going to be different case sizes, from anywhere from typically 0201s all the way up to maybe 1210s in a system like that. Now,
when you talk about the decoupling, I actually have a question for you
Sure,
on that
sure.
one. Because I remember in my early days of designing something, I would put an MLCC for decoupling on a voltage rail, and I just wouldn't get the results that I would expect. And then some older engineer would come by and tell me, hey, you need more capacitance. And you're like, well, whatever, why do I need more capacitance? And I add a capacitor and it works. Why is that a thing?
Oh,
The old drive-by engineering.
that is so what they're labeled, what you see is not what you get with Class 2 ceramics. I mentioned Class 1 are near ideal. We'll talk about those in a little bit. Class 2s are they're labeled. Let's say you buy a 10 microfarad 50 volt ceramic capacitor in the, I don't know, 1210K size or something. Well, guess what? It is really a 10 microfarad part when you measure the capacitance at a given time, maybe at about, I don't know, half a volt applied to the part at a particular frequency. If you start applying more voltage to the part, its capacitance value is going to decrease. So let's say you use it on a 25 volt line. Well, it's not 10 microfarads. It may be closer to 3 or 4 microfarads. It's going to lose capacitance because of what's referred to as DC bias. And in the case of Class 2 ceramics, the way the barium titanate is made, it has domains in it, and which have orientation to the electric field. And as the voltage goes up, the dipoles in those domains align to the electric field, and the effective capacitance decreases. This is just the way it is. You can't change it. So that's one issue that you have with Class 2 ceramics. There's another critical issue that people need to pay attention to with Class 2 ceramics, and that is aging. Now, we talked about aging in aluminum electrolytics. Aging in Class 2 ceramics is different, and it has to go back to the ceramic crystalline structure of the barium titanate. When we fired that ceramic, in ceramics, when you think about ceramics, it's think of it like a piece of pottery. You know, if you do gardening and you get some clay pots, and not the plastic ones, the good clay ones. Those clay pots go into an oven when they're produced, and they get fired at very, very high temperatures, and the ceramic sinters together. It kind of fuses together and it gets very hard. Ceramic capacitors are manufactured the same way. So when they're sintered and they turn into the structure, the crystalline structure of the barium titanate is going to be cubic, and then over time it's going to relax into its natural state, which is going to be tetragonal. And when this process occurs, what happens is that the dielectric constant of the barium titanate is going to decay over time, called aging. And so therefore, if you measure the capacitance under a set condition at time 0, it's going to read a certain value. And then if you measure it, I don't know, a few months later, a few years later, 10 years later, as you go out in time, the capacitance value will become lower and lower and lower because the crystalline structure of the part is changing. We actually have some tools and information on our website that helps the designers see how the part is going to change over time. This is only for barium titanate based parts or Class 2 ceramics. This does not apply to Class 1 ceramics.
So I guess that brings me to a question then. Now, at the age where we start seeing higher and higher switching frequencies for power supplies, we see more and more implementation of gallium nitride, silicon carbide technology. And oftentimes I see that capacitors like ceramic are built around into those areas. So what technology do I choose for those types of applications?
So we talked already about decoupling and filtering. There is another few applications that ceramics are used, and for those applications, we're going to use Class 1 ceramics, which do not have aging. They don't have DC bias, and again, they will act as nearly perfect capacitors. And That's the calcium zirconate-based system. Those areas are going to be resonant circuits. In power supply conversions today, one of the dominant architectures is the LLC system, where we have an intermediary stage in the power supply, and it resonates typically at a relatively high frequency. And in order for something to resonate, you want to have a capacitor side and something that's has inductance. It could be a transformer or a transformer with an inductor, and the electrons oscillate back and forth, back and forth, back and forth like a swing. Those systems, you need to have very stable capacitance, and you're going to either use Class 1 ceramics or you're going to use polypropylene film. We haven't talked about film yet. And there's pros and cons. Ceramics are ideal if you are at 100 kilohertz resonant frequency or higher, because of the loss properties of the ceramics are extremely low at at those frequencies, 100 kilohertz and higher. So that's one area. The other area would be where you have extremely fast DVDTs. You mentioned silicon carbide and gallium nitride. The reason why those technologies have advantages over regular silicon for semiconductors is because they have much larger band gaps, where the orbits of the electrons floating around can jump from one level to another. That band gap, energy band gap, is much bigger for wide band gap. As a result, that allows those semiconductors to be able to switch at much, much, much higher frequencies, have a much more rapid transition, and loss in a semiconductor is tied to the transition rate. So if you have a slow transition, you get a big area under there, that's all wasted energy. If you have a really rapid transition, there's no area under that, it's much more efficient. And also they can operate at higher temperatures. Because of those rapid transitions, you need to filter out those transitions, and you also, in some cases, use snubber caps to kind of reduce any overshoot. You need a technology that can handle those transitions, and the best technology out there is going to be, again, your Class 1 ceramics, superior to Class 2s. Class 2s don't like that very rapid transition because they're piezoelectric, so they have electrostriction. So if you rapidly change the voltage, they will physically change slightly in mechanical dimensions, and if you do it really rapidly, you can shatter the part. I've actually seen parts shatter. Class 1s won't do that. So very rapid transition, the best technology out there to handle that is going to be Class 1 ceramics. And also for resonant circuitry, the best technology out there, especially when you're above 100 kilohertz resonant frequency, is going to be Class 1 ceramics.
So, Peter, as we get to the end of this podcast, what would be a good way for me to figure out what the right capacitor is for me? Is there a tool that we have available that I could utilize to check my capacitor before I actually implement that in our design?
So we actually have a few tools. The first one is originally it was called KSIM, and it's morphing into what we call YSIM for YAGEO. That gives you access to all of the properties of not only ceramic capacitors, but our other capacitor technologies as well. And so you can see what it does, whether it's aging for Class 2s, whether it's DC bias for Class 2s. You can look at the amount of current you can put through a part, particularly for the Class 1s for resonant circuitry. So it gives it's a very simple user interface to access a lot of this information that really is not included in the data sheet. And then we are releasing a new tool, which is referred to as the Power Array Calculator. And this is specifically designed for engineers working on that LLC resonant circuitry to come up with the right combination of parts for the capacitor bank that is ceramics based. Makes it really easy. It factors in the amount of current going through the part, the amount of heating that's going into the part, and the voltage, and it really simplifies something that may take extended hours of manual calculation into put in your parameters, hit the button, presto, you've got several options that are your good recommended candidates for solutions.
All right, well, today we talked about MLCCs. We took a deeper look into what technologies are there, X7R, COG, ceramics. We talked about class 1 and class 2, what the pros and cons are of each of those technologies. And we took a little bit of a look into high frequency applications as well as higher voltage and resonant applications. So with our Capacitor Confessions series here, we are trying to take a deeper look into each of those technologies and find good application areas. Next week, we are going to talk about the film capacitors. And until then, keep on asking why.